Dear students, under the lecture series on complex analysis, we are going to see problems on differentiability at every point. Now, here we have the question to prove that f of z equal to e power x cos y plus I sin y is differentiable at every point. Now, in order to prove that a complex function is differentiable at every point, we need to prove two conditions, that is, the necessary condition and the sufficient condition for a function to be differentiable at every point. So, let us see what are the necessary and sufficient conditions first. So, now the conditions for differentiability of a function at every point is, the first necessary condition is the CR equations must be satisfied. We have learnt about the Cauchy-Riemann equations, and these equations must be satisfied by the complex function. And the sufficient condition is the real part u, the imaginary part v, and their first order partial derivatives with respect to x and y, that is ux, uy, vx, vi. All these functions must be continuous at every point. If these two conditions are satisfied, then we say that the complex function is differentiable at every point. Now, in order to prove this problem, we have to check for the necessary condition first, for which first we have to write the function u. What is the function u? It is the real part of f of z. So the real part of f of z is e power x cos y. So multiplying these two. So e power x cos y. In a similar manner, we have to write the imaginary part, that is the function v. So v is equal to, what is the imaginary part? It is e power x multiplied with sin y. So this is the imaginary part. Now we shall find the first order partial derivatives of these two functions. So first is to find ux, that is we have to differentiate u partially with respect to x. Y will be treated as constant, and differentiation of e power x is e power x only. So we get e power x cos y. In a similar way, we have to find uy, that is to differentiate u partially with respect to y. X will be treated as constant, so e power x remains the same. The differentiation of cos y is minus sin y. So minus sin y. We have v here now. We have to find vx. That is e power x. Differentiation of e power x is e power x only. Sin y will be treated as constant. Next we have to find vy. So to differentiate v partially with respect to y, x will be treated as constant and therefore e power x remains as it is. Differentiation of sin y is cos y. Now let us check for the CR condition whether this satisfies. We see that ux is e power x cos y and vy is also e power x cos y, which implies that ux is equal to vy. In a similar way, uy is negative e power x sin y and vx is e power x sin y. We see that uy is equal to minus, since we have a minus here, minus, and this is vx. So we have proved the CR equations. So therefore the given function satisfies the CR equation and hence the necessary condition is satisfied. Now let us check for the sufficient condition. Now the sufficient condition is we have to show that the function u, v and their first order partial derivatives are all continuous. Now if you see, the function u is a product of exponential function and trigonometric function. We know that exponential function is, all the exponential functions are continuous. In a similar way, trigonometric functions are also continuous. And we also know that the product of two continuous function is continuous and hence u and v are all continuous. In a similar way, the first order partial derivatives ux, uy, vx, vy are all product of continuous functions and hence u, v and their first order partial derivatives are continuous and therefore the sufficient condition is also satisfied. Now let me put that into words, whatever I said now. So I have written that here All exponential functions are continuous. Trigonometric functions are also continuous. And product of two continuous function is also continuous. Using this, we say that the functions u, v and the first order partial derivatives ux, uy, vx, vy are all continuous at every point. Hence, the necessary condition and the sufficient condition is satisfied, and therefore the given function f of z is differentiable at every point. So I have written that, therefore f of z is differentiable at every point. Hence, we have proved the given problem. I hope you would have understood this problem. We will see some more problems of the same type. Now here we have the second problem under this topic. We have to prove that the given function f of z equal to sin x cos hy plus I cos x sin hy is differentiable at every point. First, we shall check for the necessary condition. So from the given question, u is equal to the real part of f of z. So it is sin x cos hy. And then v is equal to the imaginary part of f of z. So cos x sin hy. So now from this, ux is equal to, now we have to differentiate u partially with respect to x. Cos hy will be treated as constant, so it will remain as it is after differentiation. The differentiation of sin x is cos x, and this remains the same. Next we have uy. So we have to partially differentiate u with respect to y. So sin x will be treated as constant, so it will come as it is, and the differentiation of cos hy is sin hy. So remember students, the differentiation of sin hy and cos hy will be, that is for cos hy, the differentiation is sin hy, and the differentiation of sin hy is cos hy, and you do not have a negative sign. Usually students confuse in that. We only when cos x is differentiated, we get minus sin x, whereas for hyperbolic function we don't get the negative sign that we get for a trigonometric function. So remember this. Now next is vx, to differentiate partially with respect to x. So when we differentiate v with respect to x, sin hy will be treated as constant, and the differentiation of cos x is minus sin x, and sin hy comes as it is. Differentiation of v with respect to y is equal to, cos x will be treated as constant, so it comes as it is, and the differentiation of sin hy is cos hy. Now we shall check the CR equation. We see that ux is cos x cos hy, and vy is cos x cos hy, and we observe that ux is equal to vy, and also uy is sin x sin hy, which is equal to minus vx, because vx is minus sin x sin hy. They are same, but you have a negative sign here, so it is minus vx. Therefore we have seen that the given function f of z satisfies the CR equation, and hence the necessary condition is satisfied. Next we will check for the sufficient condition. So for the sufficient condition, we have to show that u, v and their first order partial derivatives are all continuous at every point. Now we see that u is a product of two functions, where one of the function is trigonometric and the other one is hyperbolic. We know that trigonometric functions are all continuous, and we also know that the hyperbolic functions are continuous. And we also know that the product of two continuous functions is continuous, and hence u becomes continuous. In the same way, v, ux, uy, vx, vy all become continuous. Now let me put that into words. So I have written that here, trigonometric functions are continuous, hyperbolic functions are continuous, and the product of continuous functions are continuous. And therefore we see that u, v, ux, uy, vx, vy are all continuous. At every point. Therefore, the given function f of z is differentiable at every point. Hence, we have proved. Since it has satisfied both the necessary condition and the sufficient condition as well. We have one more problem in this video lecture. Now, f of z is equal to z cube. We have to prove that it is differentiable at every point. First of all, we will rewrite this problem. So f of z is given to be equal to z cube, which is equal to x plus iy the whole cube, because we know that z is equal to x plus iy. And using a plus b the whole cube formula, we get this to be x cube plus 3x square multiplied with iy plus 3x I square y square plus I cube and then y cube. So this is further equal to x cube, and if you see this term I square is negative 1, so it is minus 3xy square, so minus 3xy square. Since I want to gather the real part, I have done this. And here we know that I cube is equal to I square multiplied with I square is negative 1, so it is minus I. So therefore in these two terms I can be taken in common, and you will be having here 3x square y minus y cube. We have done many problems of this type. You may also go through it for better understanding. So anyway, we have separated this into real part and imaginary part, and we have obtained what is u and what is v. Now in order to check the differentiability at every point, we have to show that the function satisfies the necessary condition and the sufficient condition as well. So first we will check the necessary condition. So I have separated the real part and imaginary part, and I have written. So we will find ux, which is equal to 3x square minus 3y square. This is because we are differentiating partially with respect to x. Differentiation of x cube is 3x square, and the differentiation of 3xy square, y square will be constant, so it comes as it is. 3 also comes as it is. Differentiation of x is 1. That is how we got this. Uy is partially differentiating u with respect to y. X cube will become 0 since it will be treated as constant. Now differentiation of y square is 2y. We have minus 3x here. So 3 2 times is 6. So minus 6xy. This is what we obtain. And then we have vx, which is equal to differentiating v partially with respect to x. So differentiation of x square is 2y. It gets multiplied with 3. Differentiation of x square is 2x. It gets multiplied with 3, and so it becomes 6x. So 6xy, and differentiation of y cube is 0. And then vy we have to find. To differentiate v partially with respect to y, x will be treated as constant. So 3x square will come as it is. Differentiation of y is 1. So 3x square minus differentiation of y cube is 3y square. We shall now check whether they satisfy the CR equation. We see that ux is 3x square minus 3y square. Uy is 3x square minus 3y square. So therefore ux is equal to vy. The first condition is satisfied. And then uy is minus 6xy. Vx is 6xy. We see that uy is equal to minus vx. So uy is equal to minus vx. The second condition is also satisfied. Therefore, both the CR equations are satisfied, which means that the given function satisfies the necessary condition. Next, we shall check for the sufficient condition. The sufficient condition is we have to check whether the function u, v and their first order partial derivatives are all continuous. We see that u is a polynomial and v is also a polynomial. We know that a polynomial function is continuous at every point. In a similar way, the first order partial derivatives are all polynomials, and hence since the all are continuous, we say that u, v, ux, uy, vx, vy are all continuous. And therefore, since the necessary condition and sufficient condition both are satisfied, we say that the given function f of z is differentiable at every point. Hence, it is proved. In our next video, we will see problems on topic nowhere differentiable. That is, a function f of z is said to be nowhere differentiable. So, in order to prove that a function is nowhere differentiable, it is only enough to prove that the CR equations are not satisfied. So, if the CR equations are not satisfied, then we can immediately conclude that if the function f of z is nowhere differentiable. We will learn how to solve these problems in our upcoming video. So kindly follow the upcoming video lecture. Thank you.